All right, now let's compute that confidence interval we're looking for. This is going to be a two-sided confidence interval. That means I want to have estimates on both sides. I want to be able to say sigma squared is probably not much smaller than some quantity and probably not much larger than another quantity. In other words, let me just start by looking for confidence interval that is of the form sigma hat squared minus s up to sigma hat squared plus s. OK, and with a shape like this, I can try and solve for the correct asymptotic level that I'm looking for. So we want a confidence interval with a level of 1 minus alpha. That means the probability that sigma squared lies inside the interval should be 1 minus alpha in the large sample limit n going to infinity. How do we solve this? Well, we need to adjust the parameter s, right? So let us try to recover our convergence result here. So I'm just going to transform this expression here a little bit. So sigma squared being in I means that sigma squared is between sigma hat squared minus s, sigma hat squared plus s. In other words, sigma squared minus sigma hat squared is in the interval minus s up to s. And by symmetry, this is the same as sigma hat squared minus sigma squared being in minus ss. OK, now we're in a good shape. We are going to look at this and essentially try to reproduce this expression here. That means we multiply by square root n and divide by square root 2 times sigma squared. Sorry, I wanted to write the sigma squared inside. I should keep it outside the square root. And now I need to do the same transformation on this interval here, which means minus square root n over 2 times s over sigma squared up to square root n over 2 times s over sigma squared. Great. Now we know that this expression here has a limiting distribution that is a standard normal. That means the probability that sigma squared is in I is the same as the probability, or at least asymptotically the same as the probability of a standard normal being in minus QQ. So as n goes to infinity, by this distributional convergence, this is the same as the probability of z being in minus QQ, where z is a standard normal, random variable. OK, and now we need to adjust this to match a certain coverage level. Let's say I want 1 minus alpha. Then this is essentially lookup in a table, right? So I just want to find a q such that a standard normal between minus q and q has 1 minus alpha of its mass. The way to look this up is we're looking for q that is q alpha over 2, a 1 minus alpha over 2 quantile over standard normal. And the alpha over 2 comes from the fact that this is supposed to be symmetric, right? So if you look at this expression here, or this drawing here, we need to cut off mass from both sides, and we do it symmetrically. This basically comes out of the shape that I specified here, which was symmetric, minus s plus s. All right, so it remains to solve this for s. So we just expressed q in terms of s. We can just as well express s in terms of q and end up with s is equal to q alpha over 2 times sigma squared divided by square root n. There's a square root 2 here. All right, and now we found our confidence interval. it's sigma hat squared plus this expression. So just plug in s. Great. Now, it looks like we might be done. Or are we? There's one problem with this confidence interval. Do you see what it is? Right. We were just trying to give an interval for sigma squared. But now we are actually telling someone who might be interested in, oh, how certain are you that sigma squared lies in that interval you gave me? You're telling him, well, it's probably between some numbers times the actual parameter and some numbers times the actual parameter. While this might be theoretically useful, it is not very satisfactory if you just wanted to give some numbers, right? So the problem is we expressed our confidence interval in terms of the parameter that we were trying to estimate in the first place. So how do we solve this? There are a couple of ways around this problem. Here's one. We are only interested in an asymptotic confidence interval. And we already have an estimator for this quantity, so why don't we just replace this quantity by our estimator for it? We know it's consistent. And the nice thing is that convergence and distribution is compatible with this kind of plug-in estimator. And this is formalized by Slutsky's theorem. Slutsky's theorem tells us that if we have some random variables an converging to a in distribution, to some random variable a, and random variables bn converging to a constant. So this is not a random variable. This is a constant. Let's assume it's not equal to 0. Let me write this here. And this is in distribution, but we will have convergence in probability, which is stronger and will imply this. Then Slutsky's theorem tells us that an over bn also converges in distribution to the distribution of a divided by c. And it's important to note here that I need this second random variables to converge to a constant. If they do not, then, so if this is just a distribution, then a priori a theorem like this is very unlikely to hold, right? Because we don't have any information about the joint distribution of the two random variables. So what happens when I combine them, living on the same, possibly on the same probability space? Well, I don't know anything about this. On the other hand, if you actually had information about the joint distribution of the two random variables, you could very well say something. This is similar to how we use the multivariate central limit theorem to produce this estimator here, or the asymptotic distribution of sigma hat squared. Anyway, for our purposes, we know that sigma hat squared is a consistent estimator for sigma squared. That means we can essentially divide this whole random variable by sigma hat squared over sigma squared. The sigma squareds cancel out. And in turn, we obtain that the same convergence and distribution holds when I replace sigma squared by sigma hat squared here. And this allows me to replace all the arguments we've done so far and put a hat on all the sigma squareds. So essentially, we just managed to show this. So let me put here. So everything up to this point was just using the shape with an arbitrary s. And here, I was trying to produce this particular expression. So there's a hat here. There's a hat there. And now I solve for the same q. And this hat goes through. And then I finally have my confidence interval with a sigma hat there. And now this is something you can actually use to produce some numbers, right? OK, so I'm done. two things you should think about. First, what happens if I replace the 0 here by an arbitrary mu, as before? And secondly, what happens if I, secondly, what would you do to produce a confidence interval that does not depend on the unknown parameter sigma squared if you do not want to do what I just did and just replace sigma squared by sigma hat squared? Is there something else you could do? One thing you could think of is basically repeating the argument up until here without the red hat that I put in here. And then think about what this expression means. We could still solve for q. And we have an expression here that still involves sigma hat squared and sigma squared. And maybe we can actually solve for a different interval, not sigma hat squared minus s, sigma hat squared plus s, but for a different interval for which we have the same coverage guarantees.